Global logistics networks process millions of containers every day, operating on extremely tight margins. Within these massive, interconnected systems, a tiny miscalculation in consumer behavior at a single retail store can ripple backward, causing localized bottlenecks to expand across the network. To prevent system-wide failures, operations managers rely on a precise mathematical classification of incoming demand. We have to definitively separate unpredictable market signals from internal factory requirements. This brings us to a core concept in operational planning: independent demand. Correctly identifying and classifying this specific type of demand is the prerequisite for accurate inventory control and capacity planning. Demand classification is a rigorous mathematical boundary that dictates exactly how a supply chain allocates its capital and resources. In supply chain operations, independent demand is defined as demand for a product that is separate from the demand for any other item in a manufacturer's catalog. Looking at the formal definition from the ASCM perspective, independent demand is not directly tied to the demand for another item. It is driven by external market forces. The pull originates strictly from external actors. These are the end customers purchasing goods, statistical market forecasts estimating future sales, and direct incoming orders. Because the manufacturer has no operational control over these external customers, the exact volume and timing of their purchases cannot be known in advance. The demand is inherently unpredictable. This unpredictability establishes the boundary line for an organization. It is the exact point where mathematical certainty over internal production ends and probabilistic planning begins. The Association for Supply Chain Management provides a strict framework for handling this unpredictability. Their first operational rule is straightforward. Because independent demand originates outside the system, it must be either forecasted using statistical models or captured sequentially from actual incoming customer orders. The negative constraint is equally important. You cannot calculate independent demand by looking at the internal requirements of other items in your system. The clearest examples are finished goods. When an external customer purchases a smartphone, that event generates independent demand. This logic also applies to spare parts, like replacement screens, and accessories pulled from retail shelves by those same buyers. The defining rule for planners is simple. If the end customer decides the exact quantity at the point of sale, you are dealing with independent demand. To fully grasp independent demand, we must contrast it directly against its operational counterpart, dependent demand. This table outlines the critical differences. Demand for an assembled car is driven by external customers, making it independent demand. Conversely, demand for the car's tires is dictated strictly by internal production schedules, making the tires dependent demand. The bill of materials governs this relationship. This diagram maps the calculation. Building one car automatically calculates a requirement for 4 tires. This creates a definitive rule. Dependent demand is calculated, while independent demand is forecasted. Confusing the two causes immediate systemic inefficiency. Applying statistical guesswork to components that can be precisely known wastes capital, while trying to strictly calculate unpredictable customer behavior leads to stockouts. Classifying an item as independent demand dictates the exact operational tools a facility will deploy. Reviewing the decision impact, managing external demand requires advanced forecasting techniques like statistical models and AI. These forecasts flow directly into the master production schedule, dictating exactly what the factory builds. This schedule cascades through the organization, determining overall capacity requirements and baseline inventory levels needed to support continuous production. But because independent demand carries high inherent uncertainty, statistical models will always have a margin of error. To absorb this risk, facilities must implement safety stock. Managing independent demand requires a combination of statistical prediction and the strategic deployment of buffer inventories to absorb market chaos. Misunderstanding these classifications leads to some of the most costly operational errors made by planners. The first myth is that all demand is forecasted. As the text corrects, only independent demand requires forecasting. The second dangerous assumption is that raw materials have independent demand. They are pure dependent demand, driven rigidly by the BOM. Forecasting raw materials introduces artificial variance into a system designed for exactness. If the schedule calls for building a specific number of cars, guessing how many steering wheels are required serves no purpose. Misapplying statistical forecasts to dependent materials ensures you will either suffer critical shortages that halt assembly lines or trap capital in excess inventory. We can distill this framework into a binary checklist for operational planning. First, look at the spatial origin. External triggers indicate independent demand. Internal, BOM-driven triggers indicate dependent demand. Second, look at the required action. The ultimate distinction is whether you must forecast the item or calculate it. Internalizing this heuristic provides the foundation for modern production scheduling. Theoretical definitions must eventually be mapped to operational reality. Look at the inventory in your current business case. Can you mathematically classify every item into its correct independent or dependent bucket? If you misclassify them, you trigger the bullwhip effect. This chart visualizes how a small, unmanaged variance at the retail level amplifies into massive, chaotic spikes as it travels leftward through the manufacturing and supplier nodes. Consider how a tiny forecasting error at the independent demand level cascades, amplifying through your entire dependent supply chain. The accuracy of these initial classifications determines whether the downstream network operates with precision or descends into systemic inefficiency.